In 1835, Sir Charles Wheatstone discovered the prismatic decomposition of electrical lights. Now, nearly 200 years later, development has led us to take this knowledge a step further as we explore the capabilities of the laser-induced breakdown spectroscopy, or LIBS. By shedding light on what happens not in the solid but molten states, LIBS empowers us to refine our recycling processes, paving the way for a more sustainable and efficient aluminum industry. Aluminum, a versatile and essential material, permeates our lives, from the sleek frames of our smartphones to the sturdy structures that support our cities. Yet, behind its gleaming facade lies a delicate balance, susceptible to the intrusion of impurities. The impurities, often introduced indigenously as trace elements in raw materials or exogenously during processing, can silently erode the quality and properties of aluminum. These contaminants can manifest as microscopic particles, altering the microstructure and ultimately diminishing the material's strength, ductility, corrosion resistance, and conductivity. Enter LIBS, a cutting-edge analytical tool that empowers us to peer into the microscopic world of aluminum impurities. LIBS employs a laser beam to vaporize a tiny portion of the material, generating a unique emission spectrum that reveals the presence and composition of the impurities. During casting of molten metal, solidification mechanisms within our samples and trace elements from the mold tend to interfere with our results. Indeed, the time consumed by this intermediate step before analysis make this method even less attractive. However, by continuously monitoring impurity concentrations as a function of temperature in the melt, LIBS can provide clear trends we can use to identify phases never found before. With a knowledge of the composition of the melt, we can tailor the quantity of added elements to the objectives of the experiment and observe the active elemental kinetics through continuous analysis. The insights gathered from LIBS, in addition to further analysis of samples, provides more wholesome information regarding the characteristics of the impurities that can be detrimental to the properties of aluminum. Investigating these impurities and acquiring knowledge on how they form allows us to implement corrective measures to ensure the purity and quality of recycled aluminum. LIBS stands as a powerful tool to unlock the mysteries of aluminum impurities, pushing us towards a more sustainable and efficient recycling industry. By harnessing its capabilities, we can ensure that recycled aluminum retains its exceptional properties, minimizing environmental impact and contributing to a greener future. LIBS rolls up the door to new knowledge and understanding of aluminum impurities and their mechanisms. Together, we can revolutionize aluminum recycling and foster knowledge that contributes to a circular economy that prioritizes sustainability and innovation.